Welcome to the last module of this course, in which we will be dealing with what is called natural deduction. Now, natural deduction is an extension of propositional logic, and it builds off of this, but as we'll see, it has a rather different vibe to it. So before we set into dealing with natural deduction, let me start this video out with a quick basic introduction to the topic and to offer a kind of more intuitive way of looking at what it is that we'll be studying in the next few weeks. Now, as you should be well aware, in Module 3 of this course, we studied the use of a distinct method of determining whether an argument form in propositional logic is valid or invalid. And this method was, of course, the use of truth tables. And it turns out that this method is technically infallible when it is used correctly. That is, if you do everything right in terms of setting up and using your truth tables, the answer to the question, is this argument valid, is both certain and necessary. And when we get wrong answers, this is a result of user error, not the method itself. The method cannot give you an incorrect answer if you've done everything correctly. Now, despite this rather hefty advantage, in many instances, truth tables can be incredibly tedious to use. For example, if an argument form involves 5 distinct atomic formulas or simple propositions, let's say P, Q, R, S, and T, whatever those stand for, then the truth table needed to solve for this would contain 32 rows in it. And indeed, every additional simple proposition in the argument doubles the size of the associated truth table. By the time we make it to 10 terms in an argument, we are already at the point where we need over 1,000 lines to solve in our truth table, at which point the truth table becomes rather impractical as a method for solving the question of validity in arguments, particularly when the argument gets more and more complicated than this. So this is a pretty hefty limitation as well. Now, another shortcoming of the truth table method is that it does not require much in the way of actual reasoning on your part. It is simply a matter of mechanically following a simple set of directions, step by step, methodically and carefully, and then waiting to see what answer the process gives you at the end. The result is that this method does not really give us much practice in actual reasoning in an everyday way and in a practical sense that we're actually after in terms of all of this study. Now, for these reasons, it is important to examine a second technique for demonstrating the validity of arguments in propositional logic. This is a method of natural deduction, in which we will construct what are called logical proofs, or as they're also sometimes known as formal derivations. Now, not only is this method simpler and less mechanical than the methods used in a truth table, it also provides practice in symbolic reasoning. And developing a skill in symbolic reasoning can quite usefully be transferred into a skill in practical reasoning. Now, it's worth mentioning that constructing a derivation or a logical proof requires a good deal more thinking and strategy than simply filling out a truth table. Indeed, in some instances, constructing a derivation demands considerable ingenuity on your part, just like developing a good combination in chess. Now, unfortunately, the method of a formal derivation, or a logical proof, has its own shortcomings. Unlike truth tables, which can show both the validity and invalidity of an argument, derivations can only show validity. Now, what this means is that if you succeed in constructing a derivation or a logical proof, then you do indeed know that the argument is valid. But if you fail to construct a proof, this does not mean that the argument is invalid. And you're not really in a position then to assert anything about the argument's validity based on your failure to offer proof. Because sometimes the failure is due to the fact that it is simply impossible because the argument's valid, and sometimes it's simply the result of a lack of cleverness on your part. We just couldn't figure out an answer. So not being able to construct a proof doesn't tell you anything about the argument's validity. The only time we know something using this method is when we successfully make a proof, and then we can now say that the argument must be valid. This implies that in some cases, at least, when we find ourselves simply unable to construct a suitable logical proof, that we might still have to resort to the method of a truth table to sort out the question of validity. So before we get into the material properly, let's take a little time in this video to look at the basic idea of a logical proof without any of the formal mechanisms that might actually make it confusing, so that we understand precisely what it is we're supposed to be doing when we construct a proof. Now, underlining the entire method of natural deduction and logical proofs is the following fundamental basic idea. Given that we know the validity of a few selected forms of arguments, we can use these forms to demonstrate the validity of other argument forms. And a simple illustration of this procedure at this point might well be useful. In the last module, we used the method of truth tables to demonstrate the validity of numerous syllogisms. Now, among these, a few stand out for special mention. The first and perhaps the simplest of these is just the modus ponens. Now, modus ponens is technically short for modus ponendo ponens, which is a Latin expression that means simply the mode of affirming by affirming. And it's called this, of course, because in this type of argument, one reasons from an affirmative second premise to draw an affirmative conclusion. Now, I will assume at this point that you're comfortable with the basic idea of modus ponens, and so we can move on here to see how all of this is going to work in a logical proof or natural deduction. Now, if we wanted to, we could use a truth table to show that this is valid. But since we already know this, let's just jump to the point. Given that modus ponens is a valid form of argument, we can now use this form to demonstrate the validity of other potential argument forms. So let us consider this simple example. In the first premise, we simply get the letter P. The second premise, if P then Q. The third premise, if Q then R. And then finally, we draw the conclusion that R must be true. Now, of course, we could run this through a truth table. And given that we have exactly 3 terms, we would need 8 different rows to consider. However, we can also convince ourselves that this is a valid argument by reasoning about this argument in the following way. Now, the first step in this is to simply assume that all of the premises are in fact true. Remember that the concept of validity is always a hypothetical. That is, our question is, if we simply assume that the premises are true, would the conclusion be necessarily true as a result of this reasoning? If so, then it's a valid argument, and if not, it is invalid. Now, whether or not the premises are actually true is not really important to us. But what we want to do is just start with the assumption that they are true, and then see if we can show that this conclusion necessarily follows. Now, if we assume that all of the premises in the original argument are in fact true, then we know with certainty that the first and second premises must be true as well. So we know that the claim, if P then Q, has to be true, and we know that the statement P must be true. But of course, if these 2 premises are in fact true, then it would also necessarily follow that Q has to be true. We can infer this, and we can infer this necessarily. Why? Well, because it follows necessarily from the rules of modus ponens. And of course, at this point, now we know that our 3 premises, P, if P then Q, and if Q then R are true, but we also now know necessarily that Q has to be true. So again, if we assume that all of the premises are true, this would also mean that the third premise, which is if Q then R, must be true. And as we just saw, based on the rule of modus ponens, we also know that Q has to be true. And of course, as we know from the rule of modus ponens, it would also follow and follow necessarily that R must be true. So what exactly does this show us? Well, it turns out that if in fact all of these premises are true, we now have concrete proof that this conclusion does indeed follow necessarily. And it follows necessarily because it is working its way to this conclusion following the rules of valid modus ponens. And if each step in the reasoning is in fact a valid modus ponens, then in the end, the conclusion follows necessarily from the combination of these types of arguments. So let's take a look at another example and see how this might work. Another important classic form of argumentation is, of course, the modus tollens, which is short for modus tollendo tollens. And this is a Latin expression that means the mode of denying by denying. And rather obviously it is called this because in this type of syllogism, we move from a negative second premise to draw a negative conclusion. And again, we know that this is a valid form of argument. So if we look at this argument, we get if P then Q is the first premise. The second premise says if Q then R, and then the third says not R, and the conclusion that's drawn is not P. Now, granting that the modus tollens is indeed a valid form of reasoning, we can now use this to show that this particular argument that we see now must also be valid. And we can do so by way of the following reasoning. Now again, if we start with the presumption that all of the premises are true, then we're going to know that the second and third premises must be true as well. So assuming that all of the premises in the original argument are true, we now know that if Q, then R is true, and not R is true. But of course, if these two premises are both true, then it would follow necessarily that the proposition not Q would have to be true as well. And of course, this follows quite simply from the rules of modus tollens. This is simply a modus tollens, and this conclusion follows, and it follows necessarily. So what does that tell us? At this point, we now know that our three premises are true. So if P then Q is true, if Q then R is true, and not R is true. But we also know that not Q would have to be true based on the truth of these three premises. And of course, then, if this is correct, then we now know, first of all, that premise 1 must be true, which is if P then Q. And then the inference we drew from our modus tollens there based on the second and third premise, not Q, is also true. And from this, we can now infer that the proposition not P must also be true, based simply on the rules of modus tollens. And of course, that is exactly the conclusion that we're trying to defend in the original argument. And so what does that tell us? Well, quite simply, based on the rules of modus tollens put together multiple times, what we discover is that the original argument with its three premises does in fact lead us necessarily to the conclusion it's trying to draw. And so we know that this is a valid argument. And we know it's valid because modus tollens is valid, and it is simply building itself out of these particular valid small syllogistic forms. Now, as we will see, in natural deduction, each step in a logical proof depends ultimately on its justification based on a rule of implication. Now, in the end, we'll discover that there are going to be 18 different rules of inference or implication in this module. But in this video, we're going to simply look at the first 4 of these, and these should be familiar to you since we got all of them from the last module. In fact, the first 2 rules of implications are simply the ones we saw and have already used here, modus ponens and modus tollens. The other 2 that we're going to look at deal with a pure hypothetical syllogism and a disjunctive syllogism. Now, once again, I'm going to just assume that you understand these basic forms based on our work in the last module, and so I'm not going to offer much in the way of a clarification again here. Since each of these distinct rules is a valid form of argument considered by itself, then we find any conclusion that is derived entirely from their correct use will necessarily result in a valid argument. Now, the core idea of what a proof is can be summed up very clearly in this way. A proof in natural deduction consists of a sequence of propositions, each of which is either a premise or is derived from a preceding proposition by application of a rule of inference, and the last of which is the conclusion of the original argument. Now, we've already seen how this basically works in a rather informal way, with a few relatively simple examples. That's what we started the video with here. So the next step is to introduce the actual formal method that we use to construct a logical proof. Now, the first step in all of this is to simply symbolize and reconstruct the argument following all the rules of translation that were given to us in the last module in dealing with propositional logic. So you're pretty much just going to take the argument and then state it symbolically as you did in the last module. To give you an example of what this might look like, I'll just turn to the first example I gave in this video, where we have three premises and a conclusion. Premise 1 is P, premise 2 is if P then Q, premise 3 is if Q then R, and then finally we get our conclusion R stated. And notice how they are listed in order: premise 1, premise 2, premise 3, conclusion on the bottom divided by a line. The next step is to simply number each of these premises, and then write the conclusion to the right of the last premise, separated by a slash mark. So sticking to our example, notice what we do is simply change each of these to a 1, 2, and 3, listing our various premises. And then the last premise there, to the right of that, we have our conclusion, which was just R. And instead of a line separating all of these things, what we do is put a slash between the last premise and the conclusion. Now that we have the argument all set up and ready to go, the third step in all of this is to actually construct a proof. And you construct a proof by simply listing each inference you can draw from the premises, numbering them and listing them underneath the premises in a row, and then writing your justification for each line immediately to the right of the inference, basically sitting underneath the conclusion. Now, before we jump into this example, it's very, very important to understand what precisely your goal is in all of this when you construct a proof. And the goal in the end is to construct a proof so that the very last implication that you draw is in fact the conclusion that is sitting there on the right. And so when you construct your proof, what you want to do is simply continue numbering things where you left off, and then just list any inference you can draw from these premises that serves the goal of proving the conclusion that you're aiming at. And then you write your justification of each inference off to the right, sitting underneath the conclusion. So in this case, we can say as a new inference, number 4, we can derive Q as a true proposition. And then notice off to the right, sitting underneath our conclusion, this is based on the fact that we put 1 and 2 together, and we are following the rules of modus ponens. And so the actual inference or justification of this inference would just be 1, 2, and then MP to represent modus ponens, or whatever particular example you end up using to derive the conclusion you're aiming at. And then, of course, based on proposition 3, which was a premise, and then number 4, which was an inference that we had drawn, when you put these together, following the rules of modus ponens, what we end up with is quite simply R as an inference that must be true. And again, the end game here is to have the final line in all of your inference be whatever the conclusion is. This constitutes proof of the argument's validity. And in this case, of course, what we're talking about is R. R was the original conclusion of the argument that we were trying to prove. And so when our inference is listed with justifications end with that particular conclusion, we now have proof that this is a valid argument. So let's try another example. Now this one's a bit more complex, but it works. Premise 1 says it's either P or it is S. Premise 2 is if P then Q. Premise 3 is if Q then R. Premise 4 is not S, and the conclusion drawn is simply R. Now the first step in all of this then is to list each of these premises with a number, and then simply place the conclusion off to the right-hand side divided by a slash, so we have that separate column of justifications. Now in this example, there are actually a couple different places you might start, but we'll just start at the top. If we take premise 1, which is either P or S, and then combine it with premise 4, which says not S, we can draw the conclusion that P must be true based on the rules of a disjunctive syllogism. Leaving P alone for now, we can also draw the conclusion that if P is true, then R is true, based on the rules of a hypothetical syllogism combining premise 2 and premise 3. If premise 2 says if P then Q, and 3 says if Q then R, the logical implication of this, following the rules of a pure hypothetical syllogism, is that if P is true, then R must be true follows. And from here, we can simply take both of these new inferences, number 5 and number 6, and from this draw the conclusion that R is true, based simply on the rules of modus ponens. And of course, that was our goal, which means that R does indeed follow necessarily from the premises, and this implies that the conclusion drawn is in fact valid. Now, of course, things can get far more complicated than the examples I've already given you, but in the end, this is really all there is to constructing a proof. At this point, what we simply need to do is keep adding to the rules that we have to work with until we have all 18 of the rules laid out clearly available to us to use. But before we can do this, before we can start adding to the rather long list of different argument forms, I want to highlight a very important point about using the rules in your proofs. As you will quickly learn, it is not always easy to recognize that an argument you are looking at is in fact in the form of any of the particular rules that we've been given. As Hurley proposes, the successful use of natural deduction to derive a conclusion from one or more premises depends on the ability of the reasoner to visualize more or less complex arrangements of simple propositions as instances of the basic rules of inference. The point here is exceptionally important, as ordinary arguments will rarely show up in a form that is immediately recognizable as one of our various rules of inference. And so we have to be able to look at something that shows up in complex, confusing ways and understand that in the end, it's just something like a modus ponens or a modus tollens or a disjunctive syllogism and the like. Now, one way to recognize this point is to simply look at how we have constructed the original rules of inferences in these four forms: modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. Notice in each of these cases, we are expressing the basic form of reasoning using lowercase lettering. And of course, there's a reason for this. If you remember, lowercase letters are meant to be placeholders for any sort of statement, whether it is simple or complex. And so when you see a lowercase p, for example, it can represent most anything. P could represent simply a simple proposition like A. It might represent A and B. It might represent A and B or C, or whatever. It can represent pretty much anything. And of course, all we're saying is that side of our operator has some particular truth value. Now, to put this point in terms of some more concrete examples, if we look at the generic formula of a modus ponens, what we are looking at in this form of argument can be explained by reference to the original conditional statement and its corresponding terms, the antecedent and the consequent. Notice that the second premise of the argument, whatever that is, whether it is a simple or complex statement itself, is going to affirm the antecedent term as true so that we can affirm the consequent as true in the conclusion. Now, it's important to recognize what it is to affirm these terms, and it means that it must always be relative to the original proposition in the conditional statement. If we look at the example given on the right, notice that it does not on the surface look much like a modus ponens. After all, a modus ponens has no negations in it, and this one has 4. But once we think about precisely what the antecedent is and the consequent is in this particular argument, we can start to see this as fitting into the base pattern of our modus ponens. And of course, the antecedent of this argument is the entire complex statement, not A. And the consequent is the entire complex statement, not B. And of course, once we recognize what the antecedent is, that it is not A, notice the second premise does in fact affirm it as true, because the entire statement is not A and it agrees with it. It is essentially telling us, yes, indeed, not A is in fact true, and that is what it is to affirm in this case. And the same thing is basically true of the consequent side and the conclusion that's drawn there. And of course, things can get far more complicated than this. And if you look at this particular example, it looks like quite a mess. But in the end, if you pay close attention to it, it is really just doing exactly what the last argument did. It is following the rules of modus ponens. With a bit of squinting and some careful consideration, you can actually see this argument for what it is. notice that the antecedent in this original conditional statement is K is true if and only if E is true. The consequent is if not B, then C. And of course, the second premise and the conclusion are indeed following the pattern that we're looking for. We affirm the antecedent in the second premise, and we affirm the entire consequent in the conclusion. Now, the point of all this is that you will often find yourself looking at arguments that at first glance don't seem to fit into any of our forms. But if you take the time to think through it, you will often find that you're looking at something that ends up being much, much simpler than it appears. For example, all of these instances, as complex and messy as they seem to be, are in fact just some form of a modus ponens. But it takes some thinking and some time to see how exactly they fit into this pattern. To offer another example of the same point, if we look at our classic form of a modus tollens, we can find much of the same is going to be true. Once again, we can explain this by reference to the original conditional statement and by focusing our attention on the antecedent and the consequent of the proposition. And notice what the move is that we're looking for in a modus tollens. In a modus tollens, what you want to see is that the second premise is going to work by denying the truth of the consequent, whatever the consequent might be, in order to deny the truth of the antecedent in the conclusion. And so if we look at this particular example, given on the right, once again on the surface, it doesn't seem to fit the pattern of a modus tollens. Both the second premise and the conclusion are affirming propositions instead of negations. But once we start to think about precisely what the antecedent and the consequent are in the argument, we can start to see this as fitting into the base pattern of our modus tollens. And the reason is, of course, that the antecedent term in this case is the entire compound proposition, not P, and the consequent is the entire compound proposition, not Q. And of course, if I want to deny these terms, what I need to do is disagree with them. And if you simply look at the second premise and the conclusion, that's exactly what they're doing. If the original claim is not Q is true, to disagree with it, I would have to say you're wrong, Q is in fact true. And if the original claim is not P is true, then I can disagree with it by simply saying P is in fact true. And of course, the same would be true in this particular instance, even though on the surface, it is hard to know exactly what to make of this. But if you pay close attention and you think about it long enough, it eventually becomes clear that this fits into the pattern of a modus tollens. Now, once again, the point of all of this is that you will often find yourself looking at arguments that at first glance just don't seem to fit into any of our particular forms. But if you take the time to think through it, you will usually discover that you're looking at something that ends up being much simpler than it appears. In this particular instance, all of these are instances of modus tollens, but it takes a lot of thought to see exactly how they fit this pattern. And of course, this core point will be true of all of our rules of inferences, including pure hypotheticals, disjunctive, and all the others that we'll see soon enough here. Now, the last point to make in this video is to discuss some basic strategies to think about as you start to work through constructing proofs. Now, the first point to make is less a strategy than it is just a rule about constructing proofs. So I'm going to call it strategy 0 so I don't deviate too far from the book. The basic claim is this: never write something down in a proof unless it has a clear purpose. As Hurley notes, ideally, we should never write down a line in a proof unless we know why we are doing it and where it leads. Typically, good proofs are not produced haphazardly or by luck. Rather, they are produced by organized, logical thinking. It's useful to keep a piece of scratch paper handy and to make notes and keep track of things, but in the final product of your logical proof, you should have a clear reason for each and every step of the proof as you go through it. So the first strategy, something to keep in mind as you start working through proofs, is that it's usually smart to start by looking to see if you can find the conclusion in your premises somewhere. So you'll know what your conclusion is. It comes at the end. It's all set off to the right. The first place to look to see if you can find a hint as to where you should be taking this argument is to go find the premise that contains that thing in it. Once you do, usually strategies will start to suggest themselves. Notice in this particular example, our conclusion is R, and that's contained in the third premise, which is a conditional statement, if Q then R. And in order to get from this premise to the conclusion of R, the most likely route is going to be by way of a modus ponens. And that means that in some way, I'm going to have to try to prove that Q is true. And so you can start to just reverse engineer your thinking from simply the starting point of figuring out where your conclusion shows up in your premises. Or to offer a different example, notice in this particular case, the conclusion here is contained in the second premise, which is a disjunctive statement. And so we're probably going to need to start thinking about how we can show that not Q is true, since that's how we would end up using a disjunctive syllogism to resolve itself into the conclusion we're after, which is S. So again, usually a really good starting point here is to look for the premise that contains the conclusion in it, and then just basically reverse engineer the proof from there. Now the remaining strategies are going to focus their attention on each of our four different rules of inference that we've seen so far. So our modus ponens, modus tollens, disjunctive syllogisms, and hypothetical syllogisms. And what they'll do basically is just point out obvious features of these different types of syllogisms in terms of how you should consider using them while you're reverse engineering a proof from the basic conclusion you draw. Now the second strategy here then deals with the modus ponens, and it says, if the conclusion contains a letter that appears in the consequent of a conditional statement in the premise, consider obtaining that letter via modus ponens. Notice in this example that the conclusion is R, and in the third premise we get a conditional statement that says if S then R. Notice that the R in that conditional statement is our consequent, and if we're trying to draw out R as a conclusion from this, the most obvious path to do that would have to be a modus ponens, which means at some point I'm going to need to find a way to verify or justify the claim that S is true. Because a modus ponens would basically say if S is true, then R is true. S is true, therefore R is true, and that's how we would get ourselves to that conclusion of R. The third strategy here deals with our modus tollens, and basically everything here is more or less the opposite. If the conclusion contains a negated letter that appears in the antecedent of a conditional statement in the premise, then we should probably end up using a modus tollens to get to our conclusion. So as a simple example, notice our conclusion here is not S, and in premise 3 we have if S then R. And of course notice, if what I'm trying to do is draw the conclusion not S from that premise, what I would have to do is somehow negate R or show that not R is the case. Because a modus tollens is going to say if S is true, then R is true. Not R in the second premise would lead us to the conclusion of not S. So notice the idea here again is understanding how a modus tollens works will allow you to figure out exactly where you're going to have to go with this. What you need to look for is a negation of that claim in the antecedent of some particular conditional statement. And of course, if our original claim in the conclusion is not S, the negation of this would be the affirmative statement S is true. I'm rejecting it. I'm saying I disagree with it. The next strategy deals with our hypothetical syllogisms. And notice in this case, what we find is that if the conclusion given is a conditional statement, odds are pretty dang good that the way you're going to have to get a conditional statement as a conclusion is by way of a hypothetical syllogism. That's how they usually end up concluding themselves. And notice, of course, in this particular instance, our conclusion is if P then S. And in order to get there, what I would have to do is find a way of connecting P and S together by way of two different conditional statements. And in this case, we're going to have to do, this by a process of mixing two different hypothetical syllogisms with their inferences together. And of course, the final point here deals with our disjunctive syllogisms. If the conclusion contains a letter that appears in a disjunctive statement in its premise, then consider using a disjunctive syllogism to get to that conclusion. In this particular example, the conclusion we're trying to draw is that S must be true. And of course, when we look for the premise that contains that term in it, we find it in the second premise, which is it's either Q or it is S. And of course, from a disjunctive statement Q or S, in order to draw the conclusion that S must be true, I'm going to have to find a way to negate Q. So I need to somehow prove that not Q is the case. So that pretty much sums up the initial introductory ideas in all of this. What we've seen so far is what the purpose of a logical proof is, what you're supposed to be doing or what the goal of a logical proof is, how we actually set them up in a formal way, and then we've actually looked at 4, and so far only 4, of our rules of inference. What we're going to do basically for the next few modules is just keep adding to these rules of inferences step by step, and then building onto this complexity in order to deal with proofs in a much more serious way.